Okay. Now, before we start with our lecture today, let me just give you the following announcements. The first one, and I hope and I just believe that you are aware that the test dates now are out, because I sent the list of test dates yesterday, if it's not on Tuesday, if it's not on Monday, sorry. But anyway, if you have not yet checked your blackboard, let me just remind you about the test dates. So test number 1 is going to be written on the 16th of March 2022. That's next month. As I have already indicated that before you write any test, you have to write a quiz. So you're going to write your first quiz on the 9th of March, a week before you write your test, okay? And then test number 2 is going to be written on the 22nd of April, 2022. And likewise, you're going to first write your second quiz first before you write your second test on the 13th of April, 2022. Let me repeat. First quiz is on the 9th of March, 2022. First test is on the 16th of March, 2022. Quiz number 2 is on the 13th of April, 2022. And then test number 2 is on the 22nd of April, 2022. So please, those days are very important. So let me just again thank those people who send me the names of class reps. And again, I send it to all of you on Blackboard. So far, I think you know the names of the class rep and assistant. The last thing that I want to share with you is about tutorial. Like I said last week, we are going to have our first tutorial today from the 1450, 10 to 3 until 16:30, 4. If you have any question about the tutorial, please come with them so that you can try to address them. So those are the things that I wanted to highlight before I start giving you the lecture. Now, let's quickly go to the work of today. Okay, let me just go to the work of today. Gosh. What is this now? Okay. Here you are. Can you be able to see my screen?
Yes.
Anyone? Okay.
Yes.
Okay,
Sir,
thank you very much.
sir, the quiz will be
Yeah.
online or venue based because we know for
Eh,
the test is venue based. So asking for the quiz.
yeah, I think the quiz is online for now, because I got the information from the HOD. They said the quiz is online, but the test is face to face.
Oh,
so far.
okay, thanks, sir.
Okay. Now, let's start with our lecture. Today we are going to talk about stochastic processes. It's about stochastic processes. Like I said, we are going to refer to our lecture notes. For those who are using the lecture notes, you can just refer on page 22, 2.5. Okay. So you can refer there. So it's lecture number 5, I suppose. And then we're going to talk about
Sir,
stochastic processes. Okay. Yes, yes,
sir,
yes.
sir.
Yeah. I gave you the opportunity. You can talk.
Last time we were calculating the convolution of two filters. So how do we
Yeah.
calculate the convolution of three filters?
Okay. So may you please just wait for that question. You're going to ask it maybe during the tutorial. Is it fine?
Okay, no problem, sir.
Oh, okay, sure.
Sure.
Okay, lecture number 5 is about stochastic processes. Stochastic process. The question is, what is a stochastic process? A stochastic process is a sequence of random variable xt, okay, that start from 0, 1, 2 up to infinity, okay, where x0 represents the value of the process at time t equal to 0.
Sir,
Okay. Yes?
sir,
Yes, you know.
I can't see what you're writing.
You can see it.
Yeah, you
Me too, sir. Yeah. Eish.
They are
Just
I
invisible.
can't.
I just did
We can see, sir.
Sir,
We
you
can
must
see.
refresh.
Maybe it's their network.
I don't see. I just see variable.
No. One person at a time, please. Are you saying it's invisible?
Yeah, writing is bad.
Oh, my writing is bad. Oh, okay. Let me just try to make it visible.
Can you please write that?
Okay, it's fine. So you can't see anything there.
Yes.
No,
Just see
Your handwriting
No,
writing
is
sir, we can
bad.
see.
some can see, but some can't.
Some can't.
I
Okay.
just see a blank page, but I can hear that says writing.
When I
maybe
run it, blank.
I need to refresh
maybe
the page.
Are you telling me you can't see
Refresh.
what I'm writing?
You can
How
see
you
it.
can refresh? I can't see anything.
writing is bad. And you can see.
It's okay. Can we agree on this? It's all of you who can't see this.
Nah,
All
it's
of
not
you
all
don't
of
see this.
us.
No, we
Wait,
can see
Not
that.
all of you, man.
right there. is bad.
Hey, it's not all of us. Some of us can see, some can't see.
I'll try to print. I said stochastic process is.
It's not all of us.
Yes, I get it. Stochastic process is a sequence of random variable xt, where t is ranging from 0 up to infinity, where x0 represents the value of the process as time t equal to 0. Now, x1 again is a value. May you please mute your mic, please? Hello, guys. Please mute your mic. Okay, thank you very much. X1 is equal to a value of the process. At time t equal to 1. Okay. So x2 will be the value of the process at time t equal to 2, and so on. Then from there you can just generalize it. Xn will be the value of the process at time t equal to n. Okay. So this is how we define the stochastic process. It's a sequence of a random variable xt ranging from 0 up to infinity, where x0 is defined as the value of the processes at time t equal to 0. X1 is the value of the processes at time t equal to 1. And xn is the value of the process at time t equal to n. Okay, I think it's clear. Now, how do we define the mean, the variance, the covariance under stochastic process? Okay, so let me just go to the second page. Is that okay? Okay.
Yeah, it's fine.
Now, for stochastic, process, okay, when you want to define your mean, so the mean function under stochastic process is defined by mu t, which is equal to the expected value of xt, where t is ranging from 0, 1, 2, up to infinity. Okay, for stochastic processes, to define your mean function, you have to use mu t equal to expected value of xt, where t is ranging from 0 up to infinity. So the variance function is defined by sigma squared t, which is equal to the var of xt. Again, your t is ranging from 0 up to infinity. Okay. So what about the covariance? The covariance function is defined by gamma st. So this symbol here represents gamma st, which is equal to the curve, open brackets, of x s x t. Okay, the covariance function is represented by gamma st. That one is gamma, is not r. Okay, it's gamma st, which is equal to the curve cov, open brackets, of x s comma xt.
Say, you said which one is gamma?
That one that looks like an r, this one, it's gamma.
Oh, okay.
Yeah. Then the curve of x xs xt can also be equal to so in other words gamma st, which is equivalent to the curve of xs xt, can also be equal to the expected value of xs minus mu s, close brackets, open brackets, xt minus mu t, not mu s, mu t, then close brackets. So this is how you define your covariance functions under stochastic processes. Okay. Now, what about the correlation function? How do you define the correlation functions under stochastic processes?
Sir, what is
Yeah.
S?
Eh?
What is script of
What is
S?
what is S?
S.
I can't get your question.
Again, T is for time. And then what is S for?
So this one S again is just represent another. There are two variables here. We are just taking two variables, even though we know that T stands for the time. We would have used maybe R, not yes, R and C. So we took S and T just because we take S and T, even though we know that T stands for the time. In this regard, you just take any two variables. It's not automatically T or S. You can take any one. So in our case, we just use S and T in this regard. Or if we just want to include what is S stand for, we can just say stand for the stochastic processes, but it doesn't have any explanation. It's just the matter of just taking two variables and put them there to show that if you are going to have two variables, how do you define your covariance functions? Okay. Now the correlation function So how do we define the correlation function under stochastic processes? Okay, let me just go to the next page because in this regard, the space is very small. Do you allow me to do that? Okay. Let me just go there. I'm talking about the correlation. correlation function under stochastic processes. So now the correlation functions is defined by it's defined by rho S T, which is equal to, remember for covariance we use gamma S and T. Here in the correlation we are going to use rho. This symbol we call it a rho like this, rho. Okay, so you have to know how to write it. So rho ST is equal to the core. That core stands for the correlation of XS XT. Okay, which is equivalent to the curve of XS XT. Okay, divided by the square root of var of XS var of XT. I think you are familiar with this. The correlation function rho ST, which is the core of XS XT, is equal to the curve of XS XT divided by the square root of the var of XS times the var of XT. That is the formula which you can use to calculate the correlation functions of ST under stochastic processes. Okay, I think we are together in this regard. So now let's go to the stationary processes. If you still recall, I told you that for the process to be stationary, you have to calculate the mean, the variance, and the covariance. If all of them are independent of t, so the process is what is stationary. So let me just show you how to calculate the mean, the variance, the covariance under stationary processes. Okay, sorry. Let's go further. Now let's say for stationary process, again we are going to define the mean, the variance, the covariance, and the correlation functions. Now for stationary process, the mean function, okay, which is represented by the expected value of, sorry, this one has to be visible, the expected value of xt is equal to mu. If you try to compare this expected value for xt with the one that we used in stochastic processes, you will see that for stochastic processes, you have a t after a mu there. It's expected value of xt, which is equal to mu t. But here is just the expected value of xt, which is equal to mu. We don't have t. Why? Because in this regard, we just assume that our mean is stationary. It doesn't depend on t. Okay. So the var variance function under stationary process is given by var of xt, which is equal to sigma squared. This symbol, we call it sigma squared, stand for the variance. Okay, so you have to know how to write it. So now the variance function is defined by var of xt, which is equal to sigma squared. The covariance function under stationary process is defined by gamma again. Gamma, this time around, is gamma k. Remember, in stochastic process we were using gamma s and t. Here, because the process is stationary, we're just using gamma k, which is equivalent to the curve of xt plus k, close brackets. Gamma k equal to the curve of xt plus k, which is equal to, in terms of the expectation, the expected value of xt minus mu xt plus k minus mu. See now, mu doesn't have t because it's stationary. This is how you define the main function, the variance function, and the covariance function. Okay. Now let's go to the correlation function. How do you define the correlation function under stationary processes? So I can move to the next page, isn't it? Okay.
Yes.
Yes.
So the correlation function is defined by rho k, because this time around is for stationary, which is equal to the curve, open brackets, of xt plus k. Okay, which is equivalent to, in terms of the expected value of, not expected value, sorry, you don't have expected value, which is equivalent to the curve, not expected value here, equivalent to the curve, okay, of xt plus k, divided by what? The square root of the var of xt times the var of xt plus k, close brackets. So the correlation functions under stationary process is represented by the rho k, which is equal to the curve of xt plus k, which is equal to the curve of xt plus k, divided by the square root of var of xt var of xt plus k. I think it's clear, isn't it? So now I've introduced for you how to calculate the mean, the variance, the covariance, and the correlation functions under both stochastic and stationary processes. Now let's go to the properties of autocorrelation or autocovariance functions. What are the properties of autocovariance functions? Properties of autocovariance function. Properties of autocovariance function. So autocovariance function in short is ACVF. So ACVF stands for the autocovariance function. So from now onward, when we use ACVF, you must know that we're talking about the autocovariance function. Okay? But now we just want to see those properties. Number one, in time series, gamma k is always equal to gamma of minus k. That is the first property of autocovariance function. Gamma of k is equal to gamma of minus k. So in other words, if somebody is calculating gamma of minus k and somebody is calculating gamma of k, so their values must always be equal. That's number one. Number two, gamma 0 is equal to var of xt. Gamma 0 equal to var of xt, which can also be equal to the var of xt plus k. Okay. This is another property.
So can you please explain the first one again?
The first one, I'm saying in time series analysis, gamma k is always equal to gamma of minus k. In other words, the person who use a process to calculate gamma k and find the value, that value will be the same as the one who used gamma of minus k. So in other words, positive and negative in time series analysis, it doesn't mean anything in terms of the values if you are calculating them. So that is why in other books, they use both plus and minus in one thing. They just use gamma sometimes equals to gamma of plus and minus k. Okay. Please. So in other books, they use it like this. Gamma k is equal to gamma of plus or minus k. In other words, when they use both plus and minus, they're recognizing that you can use all of them at the same time, or you can use them separately. It doesn't have any effect in time series. So in our case, that's why we're saying gamma k is equal to gamma of minus k. Somebody will use a minus values and another one will use positive values, you get the same answer. We just say those are the same answers. We don't differentiate them. They're the same. Okay. So now there are two properties of autocovariance functions. So now let's go to the properties of autocorrelation functions. Properties of autocorrelation function. Autocorrelation function. So now here autocorrelation functions can be abbreviated as ACF. Remember, autocovariance function is ACVF. Autocorrelation function is ACF. So what are the properties of ACF or autocorrelation functions? Number one, rho K will be equal to rho of minus K. As in autocovariance, we say gamma K equal to gamma of minus K. So here rho K is equal to rho of minus K. That's number one. Number two, rho zero.
Sir,
Yeah.
can you go back to the previous page? I want to see number A.
Okay. Number A, rho K equal to rho of minus K. And autocovariance function, gamma K equal to gamma of minus K. That's okay?
Yeah, thank you.
Okay.
Sir,
Yeah.
if I'm left behind from the stationary process of the correlation function because of network, my screen was blank.
Oh, you didn't write here.
Yeah.
You didn't write this one. So this is the what called the formula for correlation functions under the stationary processes.
Yes.
Okay. Then from there we have the properties of autocovariance functions and the properties of autocorrelation functions. So under covariance functions we have two properties: gamma K, which is equal to gamma of minus K. B, gamma 0, which is equal to the var of xt, which is equal to the var of xt plus k. And at the later stage, you will know that gamma 0 again is equal to sigma squared z, but you will know that when you come to that. So properties of autocorrelation function. Number A is rho K equal to rho of minus K. I think you get it. Can I proceed?
Yes.
Okay. So now number B, rho 0 is equal to 1. In other words, to explain this, let me just go back a bit. Here, when we talk about the properties of autocovariance functions, when we say gamma K, we're saying the autocovariance functions at leg K. So, but anyway, we will understand what is the meaning of leg K when we proceed. The autocovariance functions at leg K is equal to the autocovariance at leg of minus K. So here number B, gamma 0, the autocovariance of leg 0 is equal to the var of xt, which is equal to the var of xt plus k. Okay. Coming to the properties of autocorrelation functions. Here, rho k simply means that the autocorrelation function at leg k is always equal to the autocorrelation functions at leg minus k. In other words, if you are talking about the values, leg 1 and leg -1. So we are going to consider the positive values and the negative values. All of them are the same, are equal at time series. So here, number B, when we say row 0, we are referring to the autocorrelation functions at leg 0. It's always equal to 1. So you don't have to calculate this one. You must know if they said just calculate the autocorrelation functions at leg 0. You just say it's equal to 1 according to the property. It doesn't need you to calculate it. But if you just want to calculate it, you can calculate it. At the end of the day, you'll find it as row 0 equal to 1. Number C, row K, absolute value is always less than 1. That is the third property under autocorrelation functions. The absolute value of row K, the absolute value of autocorrelation functions at leg K is less or equal to 1. And you know that this one can also be written as row K less or equal to 1, isn't it? Greater or equal to -1. So these two are the same. The absolute value of row K is less or equal to 1, or row K is greater or equal to -1, or row K is less or equal to 1. You get it? Now, let me just go back to the autocorrelation functions and stationary process and show you. I just want to show you something. Let me just go back, please. Go back here. You see here the autocorrelation function formula, which is equal to the curve of xt, xt plus k divided by the square root of var of xt plus k. Now, if you recall, the covariance of xt plus k, if you go up again, the previous one, just want to show you something. It's not there. Okay, not here. Yeah, here. See that the var of gamma k equal to curve of xt plus k. So if you can proceed. So instead of writing curve of xt plus k, you can write what? Gamma k, isn't it? Divided by. Now, divided by the square root of var of xt plus k. But according to the properties of the autocorrelation functions, if you still remember, I said var of xt is equal to the var of xt plus k. Let me just go there so that you can understand this one. Here, you see now, var of xt is equal to the var of xt plus k, and all of them are equal to what? Gamma 0. So that means you can substitute there by what? By gamma 0, or maybe you just write var of xt all squared, because var of xt and var of xt plus k are the same. So you can just say var of xt all squared. Okay, var of xt all squared, but there is a square root there, so square root and square there, they can cancel each other. At the end of the day, you are going to have gamma k over var of xt. Okay, but you know that var of xt is equal to gamma 0, isn't it? So you can substitute that var of xt by gamma 0. So at the end of the day, you are having gamma k over gamma 0. You get that? Finally, so you can end up saying rho k here, because rho k equal to core of this one, core of that one, and then later gamma k over gamma 0. So at the end of the day, rho k, therefore rho k is equal to gamma k over gamma 0. This equation is very important. We are going to use it very often. Gamma k equal to rho k equal to gamma k over gamma 0. In other words, what we're saying is that the autocorrelation functions at leg k is equivalent to the autocovariance function at leg k divided by autocovariance function at leg 0. I think it's clear. Let me just go there where we were. Yeah, we were here. Okay, let me just go back a bit. So now this one, if you take autocovariance function, property number A is there, gamma k equal to gamma of minus k. Let's say we just want to prove that rho k equal to rho of minus k. If you want to prove that, so you are going to take the condition of the properties of autocovariance function, which is gamma k equal to gamma of minus k, isn't it? So here, if you can divide both sides by gamma 0, divide both sides by gamma 0. Okay, what do you get? Gamma k over gamma 0 is equivalent to what? To rho k. Okay. So gamma of minus k divided by gamma 0 will be equal to what? Rho of minus k.
Afternoon, sir.
Eh?
Afternoon, sir.
Okay. Yes.
Yes, sir, can you hear me?
Yes, I can. Okay.
Yes, sir, may you please help me out with something? I'm a bit confused. You said something about rho 0 being equals to 0. When does that apply? Unless if I heard wrong.
Oh, you are referring to this one. This one.
I don't think it's that. You said, okay, so it's only that one.
Yes, this is the only one. Remember, here we're talking about the properties. There will be a case where you are going to calculate those autocorrelation functions. And at the certain stage, you find that rho 0, you calculate the rho 0. So there is no need to calculate rho 0 because from the property of autocorrelation functions, rho 0 is always equal to 1. You just say rho 0 equal to 1. You will see when we do the example what we are talking about. Here we are just giving you the properties.
Oh, okay. Thank you, sir.
Yeah. But if you want to prove that rho k equal to rho of minus k, this is the scenario that I gave you. You take the autocovariance function property, gamma k equal to gamma of minus k. Then after that, you divide both sides by what? By gamma 0, like what we did here. And then after dividing it, you will find that this is equal to what? To rho k. And this is equal to what? Rho of minus k, which is the same as this one. Let me just go to the next one. So rho 0 equal to 1. So you can just prove this one as well. Remember, I told you that rho k I told you that rho k, okay, is equal to what? Gamma k over gamma 0. You still remember that one? So here, let k to be equal to 0. If you let k to be equal to 0, so, in this case, if you can let k equal to 0, so rho k now becomes rho 0. And gamma k becomes gamma 0. Then you divide by what? By gamma 0, which is equal to 1. Okay. Now, coming to property number 3 under autocorrelation function. We said absolute value of rho k is less or equal to 1, or rho k is greater than minus 1 or less than 1, less or equal to 1. Let's say we just want to prove this. And I just want to leave this one as an exercise. But I will give you a hint. I just want you to prove that absolute value of rho k
Sir,
is
before
less.
the exercise, can you please explain B and C? I lost you because of connection.
My guy.
B and C. I said B.
Yes.
Okay. Yes, I got you. B is the second property of autocorrelation function. So I said, if you just want to prove that rho 0 is equal to 1, you have to apply this formula. You understand that I told you that rho k is always equal to gamma k over gamma 0. Still remember this one from the previous explanation. So rho k equal to this one. So here, if you can let your k to be equal to 0, so the whole of this now changes to be what? Rho 0 equal to gamma 0 over gamma 0, which is equal to 1. If you want to prove that rho 0 equal to 1, this is the scenario. So number C is what I'm talking about now. I said it's left as an example, as an exercise, sorry, for you to do. You are going to prove that rho k absolute value is less or equal to 1, or you are going to prove that rho k is greater than or equal to minus 1, or rho k is less or equal to 1, that one. So, but before you do that, or you're going to do it on your own time, let me just give you a hint. How do you do that? How do you solve that? Okay. Remember, we just want to prove that rho k greater than minus 1 less 1. Hint. You are going to have two equations. Number one, you are going to calculate the var of xt plus k. Then you equate it to greater or equal to 0. Why are we saying it's greater or equal to 0? Why are we saying var of xt plus k is greater or equal to 0? Why are we saying that? Because the variance is always positive. We don't have a negative variance. I know that I'm saying this one. I know that when I'm going to ask this on the quiz or on the test or on the exam, somebody will calculate and find the negative variance. It's wrong, totally wrong. We don't have a negative variance. Are we together? But when you are confused, you are going to find the negative variance. But you must know that variance doesn't have a negative answer. It's positive. Okay. So that's number one. So this one now you take it as equation number one. Okay. Then you have another equation. Var of xt minus xt plus k. Again, it's always positive. We don't have a negative var. Then you take it as your next equation. After expanding the var of xt plus k, then you equate it to 0. Then you do the same, you expand var of xt minus xt plus k greater or equal to 0. Then you equate two equations. After equating two equations, you will get the answer there. So, but let me just give you another hint on how to calculate the var of xt plus k. I know that you know those properties of variance and properties of expectations. I know you did that in second level. If you didn't, so hard luck. So now let me just remind you for those who still recall. The var. Let me just take two variables of x plus y. Yes. Yes, I gave you the opportunity to talk.
Okay. After expanding the two equations, are we going to equate them or are we going to equate them to zero, each to zero?
No, we have already equated them to zero. They equated them to zero by this inequality. It's greater or equal to zero. So you expand the one on the left, var of xt plus k. You have to expand it, then later you equate it to zero by this inequality here. We need this inequality here. But your duty is to expand the one on the left, the expression on the left.
Okay.
So now I'm helping you. How do you expand that expression on the left? This is what I'm doing. I took two variables, a and b, or x and y. Let me just use x and y because you are familiar with this one. Let's say you have got var of x plus y. What is the answer there? Var of x plus y. The answer will be what? You can tell me.
It's var of x plus var of y.
Okay, var of x plus var of y. Why? That's the answer, isn't it? The reason why, can you give me the reason why did you say that the var of x plus y is equal to var of x plus var of y? Why? Okay, let me just assist you. If you say var of x plus y is equal to var of x plus var of y, we have a condition. The condition being that we assume that x and y are what? Are independent, isn't it? If x and y are independent, therefore the var of x plus y is equal to var of x plus var of y. That's true. It's when if x and y are independent. Are we together? So, however, if x and y are not independent, this equation fails. Okay, let me say if x and y are not independent, x and y are not independent, what do we get? The var of x plus y will be equal to what? You can tell me now. In this case, x and y are not independent. So give me the expression of var of x plus y will be equal to what? Anyone?
There is a covariance of them.
Eh? Come again? Yes, we are almost there. You said is what? You were right. I just want to get it right the way you said it.
Is that of the top plus the covariance of them? Since well,
definitely,
it is not
that's
there.
what we are looking for. So that means var of x plus y is equal to the var of x plus the var of y plus the true curve of x and y. You see now? Because x and y are not independent. So this expression holds. Var of x plus y is equal to var of x plus var of y plus 2 curve of x and y. So therefore, in the exercise up there, because x and y are not independent, I'm expecting you to expand the var of xt plus k, like what we did here. In other words, you have to include the covariance there. Then after that, you equate the two equations, you'll get the answer. Just go and try it. Talk about it later. Yes. 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 Talk.
The network is gone.
Okay, you'll come back.
Uh,
Yes.
Can you please explain it again from var in open
X plus
brackets
Y.
x plus y? Yes.
Okay. Okay. With pleasure. Let me just explain it for you. I was saying, isn't that you have to prove that rho k is greater than or minus 1 less or equal to 1? Then I said I must give you a hint. So var of xt plus k is always positive, and var of xt minus xt plus k is always positive. So then I said that, let me just remind you how to calculate the var of two variables. Then I take x and y variable. You can take a and b. You can take c and d, any variable. So in my case, I took x and y. So what is the var of the product of the two variables? Var of x plus y is equal to var of x plus var of y. So this condition holds if x and y are independent. So condition number 1 hold if x and y are independent. However, if x and y are not independent, condition number 2 holds. In other words, condition number 2, you are going to add the covariance of the two. So that is what we did here. Because they are not independent, so you have to add this. Otherwise, if it doesn't add this, so you are saying that x and y are what? Are independent. So in our case, yeah, yes. Yes.
No, continue, sir. Continue.
Okay, in our case, x and y, according to that hint there, x and y, or xt and xt plus k, those are the two variables, are not independent. So you have to apply what? Scenario number 2, this one. So in other words, you must have var of something plus var of something plus the 2 curve of something. Then from there, you just equate it to 0 using this equality here. So in your case, you're going to put this one, then later you just say greater or equal to 0. Then you work with the one on the left. So how do you deal with the one on the left? You apply all the properties that I gave you before. You apply all the properties, this one, the covariance properties, this one. You can find one of them, you are going to apply it here, there, on that exercise. The same applies to the autocorrelation function. Some of those properties you are going to apply there. Then from there, you equate two equations, you find the answer. So let me just give that opportunity for you to go and work on it. Then if you have any problem, you will let me know. Don't just come to me saying that it's very difficult without starting something. You have to write something down and then we'll assist you from there.
Sir,
I
I think you just have to do some examples.
The example?
Not only stronger, but makes strong and cheaper. Maybe
Can somebody mute the mic, please? What are you saying?
I think you should do some examples with us first. So.
Yeah, so that we can understand it.
This is the proof. It doesn't need any example. Okay, you want me to do maybe question number one? Question one.
Yeah,
Do some
or maybe
questions.
And
three,
then they will do the question number
question.
two and then you combine.
Pella, this is third, and ish.
Okay, I'm giving you this opportunity. Just go and struggle. In the next class, we are going to take to do that. I want you to go and do something so that you can understand.
Okay, sir.
Because if I can just do it for you, you are going to memorize and then it won't be good for you. It's not. It won't be good for you. You have to understand this. So, but anyway, let me give you this opportunity. Just go and try to work on it. If it's difficult, come back to me. I'm always available. Isn't it?
I don't know. Should build the answer or
Yes,
what?
I'll do it later, but not now. Later. Let's agree on
All
that.
right.
Yeah.
Okay.
Okay, now let's go to the next one. Okay. From the lecture notes, let's try to define what is the weekly stationary. Then after defining weekly stationary, we'll talk about the white noise. After talking about white noise, talk about independent and distributed noise. Then from there, we'll do example. Yeah. Let me just start with the weekly stationary. Weekly stationary process. All along I was talking about stationary process, but this time around I just added another part called weekly stationary process. So you can say weekly stationary process or covariance stationary process. Okay. Or if you don't want to use this one, you can use second order stationary process. All this mean the same thing. Weekly stationary process or covariant stationary process or second order stationary process. So the question is, what is a weekly stationary process? A process, let's say xt, is said to be weekly stationary process. Okay. If those conditions are held, the process xt is said to be weekly or covariance or second order stationary process if the following conditions are held. The first one, if the expected value of xt equal to mu. That is the first condition for weekly stationary or covariance or second order. Condition number one, expected value of xt equal to the constant. Number two, the var of xt.
Sir, go back to that page. I'm still copying.
Okay.
Yes, there is.
Please.
Okay, let me just write it here then. Condition number 1, expected value of xt equal to mu var of xt is equal to sigma squared. Let's say z. Sigma squared z. The one at the top there is 2. The one at the bottom is z. Okay. Expected value of xt is equal to mu, and then the variance of xt is equal to sigma squared z. That's condition number 2. Sigma squared z. Okay. Condition number 3, the curve of xt plus k is equal to gamma k. Okay. A process xt is weakly stationary if, number 1, the mean, the variance, the covariance, all of them are independent of t. Are we together? A process xt is said to be weakly stationary, covariance stationary, second order stationary if the mean, the variance, the covariance, all of them are independent of t. In other words, to calculate whether, or to prove whether the process is covariance stationary, you have to calculate the mean and find that it doesn't depend on t. Then you have to proceed to the variance and you find that it doesn't depend on t. You go to the last one, the covariance, and you find that it doesn't depend on t. So that process is covariance stationary. But if one condition fails, so the process is not covariance stationary. It's either a mean is depending on t, or a covariance depending on t, or the variance depending on t. So that means that the what you call the process is not stationary. I think it's clear. Yeah. Can I proceed?
Sir,
Yes.
so what you're saying is when expected value is equals to mu and variance is equals to sigma squared z and covariance is equals to gamma k, the process is stationary. It doesn't depend on
T.
or the
Doesn't
it means
doesn't depend on
stationary. Okay.
doesn't depend on t. But we are not saying that when you calculate the expected value, you have to get a mu. You get that? You can get a constant, you can get a value 1, 2, 3, as long as that value doesn't depend on t. So this one we are just giving the scenario where the mean is what? Is mu. We're giving the scenario where the variance is sigma squared z. We're giving the scenario where the covariance is gamma k. But all in all must be constant. It must not depend on t. If one depend on t, so the whole process fails. Are we together?
How do we see that it depends on t?
So that value is supposed to have t on it. If it is having t on it, so that means that that mean or variance is depending on that, on T.
Okay, thank you so much, sir. I understand it.
Okay, thanks. Now let's go to what we call a white noise. It's not black, it's not blue, but it's a white. Why do you call it white noise? You can call it a white noise process or a purely random process. A white noise process is a purely random process. Purely random process. Okay. What is a purely random process? Okay. A process ZT this time around is said to be a process ZT
Back.
Yes.
Yes, sir, please, can you go back?
No, I'm writing it again. It's the same thing. A process ZT.
Okay, all right, sir. All right, sir.
Said to be, okay. Said to be white.
Sir, can you go back to white noise process?
Hmm? In here.
You see, Jack,
What do you want here?
says the same thing.
A process that is said to be a white noise or a purely random process with mean mu and variance sigma squared z written as ZT white noise open brackets mu sigma squared z. If
Sir,
yes,
can you please go back to that page? I want to check if I'm not left behind because my network kicked me out.
I'm back now. You have them?
Yeah.
Okay.
No.
Which one? You don't have this?
Yeah, everything is fine now.
Okay. I said the process that is said to be a white noise or purely random process with mean mu and variance sigma squared z, written as zt has that symbol means has a white noise is this symbol. Okay. Zt has a white noise open brackets mu comma sigma squared z close brackets if the expected value of zt is equal to mu and gamma k equal to the power of of zt plus k, which is equal to sigma squared z, provided k equal to 0 or 0 otherwise. Okay, that is the definition of a white noise or purely random process. Process ZT is said to be a white noise with mean mu variance sigma squared z, written as ZT as a white noise, mu sigma squared z, if the expected value of ZT is equal to mu and gamma k equal to curve of ZT plus k, which is equal to sigma squared z, if k equal to 0 and 0, that expression curve of ZT plus k is 0 if k is different from 0. Here, let me just explain here this part so that you can understand it. Here we are saying, starting from here, the expected value of ZT is equal to mu. I think this one is clear. But when you come to gamma k, the autocovariance at like k, which is equivalent to the curve of ZT plus k, is equal to what? If here, instead of this k, you put 0 here, okay? You are going to have gamma 0 here, get that? Which is equal to the curve of ZT. And the whole of this, because it's curve of ZT and ZT, they are not independent. So their covariance is 0. It's the sigma squared z. Sorry. Their covariance is sigma squared z. That's what we're saying. You get that? This is what we're trying to explain. Now, let's come to the second one, this one. Okay. I don't know whether I can erase this part, this one. Can I erase this one? So that I can explain this one.
Erase.
Okay. Let me just erase so that I can explain the second one. Now, if k now is equal to 1, if we set k to be equal to 1, so therefore this gamma k here now becomes gamma 1, isn't it? And then you're going to have curve of zt plus 1. Are we together? So because these variables, this one and this one, are independent, so their covariance is going to be 0. That's what we're saying here. If k is different from 0, in other words, if k is 1, 2, 3, 4, 5, up to infinity, so gamma of that will be equal to 0. Okay, let me take another example. If we say k equal to 4, instead of putting 1 here, let's put 4. Okay, so that means here you're going to have gamma 4. Okay, here you're going to have zt plus k, 4. Okay. So again, this one and this one are independent. So their covariances, they will take you to 0. So that is why we're having this condition here. The condition that doesn't give us 0, it's only this one. It's when k equal to 0. The rest, they're going to give you 0. I think it's enough. I explain it's enough. So let me go to the next one process now. Let me just go to the next process now. The next process, we call it IID noise. Independent and identical distributed noise. Let me just go to the next page. The next one is let me use this one so that you can see it clearly. It's IID noise process. Remember, the first one was white noise or purely random process. So this one is IID noise process. What is the meaning of IID? IID stands for the independent and identical distributed noise process. So how do we define this one now? So a process ZT is said to be independent, identical and distributed noise, which is IID noise, with mean equal to 0 and variance equal to sigma squared z. If the random variable zt, oh no, I missed something here. Said a process that is said to be IID noise with mean 0 and variance sigma squared z, written as, I forgot something here, written as, we have to write it down and show you how do we write that. Written as ZT is a white noise, as a IID noise, open brackets 0, because what? The mean is 0 here. So that's why we're having 0. And the variance is what? Is sigma squared z. So we're going to have sigma squared z here. Okay. So written as this one. If the random variable zt, let's say random variables zt are independent and identical distributed with the mean zt equal to 0 and what? And the variance of zt equal to what? Sigma squared z. So this is how we define the what? The independent and identical distributed noise process. It's a process zt. The process zt is said to be IID noise with mean 0 variance sigma squared z, written as zt as a IID open bracket 0 sigma squared z if the random variable or random variables ZT are independent and identically distributed with mean 0 and variance sigma squared Z. Okay, now let's quickly go to the example, because now I think you're tired with theory thing. Let's go to the example. In a lecture notes, if you open page 21, and there is referred as an exercise 2.3.1. You see that one? Okay, let me just go there and try to write it down if you don't have it. Can I go to the next page?
Yes.
Okay. Let me say example.
Sir,
Yeah.
can you go back up for 2 seconds? I just want to finish writing the notes.
Back?
Yeah, just up. Yeah, just 2 seconds.
Okay.
Wow, I'm done.
Oh, thanks. Example, it's on page 21, lecture notes, but it's written exercise 2.3.1. Page 21. Okay. You have been given the process, time series process, xt, which is equal to 5 plus 2t plus zt. This is the time series process given, where z is defined as zt as a white noise with mean 0 and variance sigma squared z. What does that mean? This one, this condition, what does that mean? It means that the expected value of zt is equal to 0, which is this one, okay? And the variance of zt, this one, is equal to sigma squared z. I just want you to understand what is the meaning of this part. This one. That's why they say zt has a white noise with mean 0 and variance sigma squared. It simply means that the expected value of zt is equal to 0 and the variance of zt is equal to sigma squared z. It simply means that if you are calculating a certain process and reach a point where the expected value, you want to calculate the expected value of zt, you must know that the expected value is 0. Expected value of zt is 0. And you can't reach the point where you have a variance of zt, you must know that the variance of that zt is sigma squared z. Simple that. So what do we want to do here? We just want to check if this process is stationary. Or we want to check if this process is a weakly stationary process or covariant stationary process. So where do we start? The question says check whether the process is covariant stationary. Where do we start? Remember, you have to calculate the expected value, the variance, and the covariance. If all of them are independent of t, therefore the process is what? Is covariant stationary. That's it. So now let's start. Let's start with the expected value. Let me use this bigger one, the bold one, so that you can see. So the expected value of xt. In other words, you are introducing the expected value from left and right. So you introduce the expected value like this, 5 plus 2t plus zt. Then you're done. Then you continue to the second step. Okay. Expected value of xt now it will be equal to what? So the expected value of xt equal to what? So now you introduce the expectation inside there. So you're going to get what? The expected value of 5 plus the expected value of 2t plus the expected value of zt. I'm just writing everything so that you can understand. Otherwise, I would have just go straight to the answer. The question is, what is the expected value of 5? Who can tell me the answer? Expected value of 5 is what?
5.
It's 5 because it's a constant, isn't it? Plus expected value of 2t.
2 expected value of t.
2t.
2t, not a 2 expected value of 2. It's 2t. Why? Because this 2t, we take it as a constant because it has not been defined there. There, they only define what? Zt. They didn't define 2t. They defined zt. So 2t, because it's not defined, we take it as a what? As a constant. So that is why the expected value of a constant 2t is going to be 2t. Plus, what is the expected value of zt?
0.
It's 0. So therefore, our answer is the expected value of xt is equal to 5 plus 2t. So is the mean depend on t or not?
It depends on t.
It depends on t. Okay. If it depends on t, what is your conclusion? Because we just want to check whether that process is covariance stationary or not. What is your conclusion? Is the process covariance
It's not
stationary or not?
stationary.
It's
Not
not
stationary.
because it's
Stationary.
the value of expected value is depending on t. So when you tell me that the process is not stationary, you must give me the reason. Why are you saying it's not stationary? Okay. So here we are saying it's not stationary because the mean is depending on t.
Yeah.
Therefore, it's not necessary to go and calculate the variance and the covariance. We just conclude that the process is not stationary. So now we just want to make it to be stationary. What do? You still remember that I told you that there are many transformations that we can apply to make the process to be stationary. And I said we are going to use differencing in our module. So now in this time around, because the process is not stationary, we have to difference it. So where do we start? We start on the first differencing. We start on first differencing. So we difference once if and check if it's stationary. Still remember the formula for first differencing? It's changing xt equal to xt minus 1, isn't it? Now, changing xt equal to this, but you know that xt is equal to what? Xt is equal to the whole of this. So we substitute there 5 plus 2t plus zt, then minus. This minus is this one. Open brackets. Xt minus 1, where there is t, you put t minus 1. Where there is t minus 1, you put t minus 2. When there, and so on. So that means here you're going to have 5 because it's a constant plus 2 open brackets t minus 1. Okay. Then plus zt minus 1. Then close brackets. Yes.
Is the minus 1 at the bottom?
Well, because it's coming from here. Zt here is at the bottom. Yes, subscript.
Okay. Oh, yeah.
It's different from this one here. Then it's 5 plus 2t plus zt. Then you multiply through by a minus. You're going to get 5 minus 5 minus 2t plus 2 minus zt minus 1. Are we still together? Okay. Now, this cancels this one. Okay. This cancels this one. Then we are left with those other ones. So you're going to be left with what? 2 plus zt. So you won't see minus zt minus 1. Let me just rewrite it there in the next page. 2 plus zt minus zt minus 1. It's like this, isn't it? Now, this is a new process. This is a new process. Now, again, to check whether this new process is stationary, you do what? You apply the same scenario. You apply you calculate the expected value, you calculate the covariance, you calculate the variance. If all of them are independent of t, so this new process here is what is stationary. So let's do it. Expected value of change in t, expected value of 2 plus zt minus 1. Okay. So the answer here is true. Now it's constant, doesn't depend on t. So you continue to the what? To the next one, the variance. I'm very fast now because the time is up. Var of 2 plus is that not 2, this one? zt minus 1. And the answer here, the variance of the constant is 0, you know that. And the variance of zt is sigma squared z. So, and the variance of zt minus 1 again is sigma squared z. So here you're going to have sigma squared z plus sigma squared z. And the answer is what? 2 sigma squared z. So you can see that it doesn't depend on what? On t. So it's constant. So you proceed with the what? The covariance. The curve of changing xt, changing xt plus k is equal to what?
Sir,
Uh,
sir,
mm-hmm.
isn't it the var of the negative like the zt minus 1?
Yeah, you're quick to forget. I told you that we don't have a negative variance. You forgot.
Oh, okay.
You know what
Yes.
we do here? Just because I skip some of the steps. Here, because you are having, let me just write it here. I knew that you will ask this. The var, isn't that you are finding the var of minus zt minus 1. Okay? The var of zt minus 1. So this one, here you have 1 here. It's a minus 1 here. Then when you square it, it's going to be a percent, isn't it?
Sir,
Mm.
sir,
Yes.
can you go back to the previous page? I had network problems.
Which one? We don't have time now. You are going to download this. You're going to download this. You don't have time. Let me
Okay.
just finish this one. Cover. So change in xt is the whole of this, isn't it? So it's 2 plus zt minus zt minus 1. This one. Then cover. Then change in xt plus k. So you're going to have 2 plus zt plus k. Where there is k, put plus k. Then minus zt plus k minus 1. Because all of them, they are independent, so their covariances are 0. So therefore, at the end of the day, the curve of change in xt plus k is equal to 0. So your mean is constant, your variance is constant, your covariance is constant. So therefore, the process change in xt, you don't say the process xt. This time around, you say the process change in xt is covariance stationary.
Sir,
Then stop. That time is out.
sir, how did you conclude the covariances are 0? Do not.
I said they are what to call it? Their variables are independent. If the variables, when you multiply two variables that are independent, so their covariances is 0. I thought maybe you did this on your second level.
Oh, I can see what you're talking about.
You can see, ne? Yeah. So just go and check it. It's going to give you 0. But you will understand this better when we do a lot of exercises or a lot of examples, because we are still going to do a lot of examples. Let me stop here because our time is already.
Okay, so can you just go back? I want to screenshot.
Okay. Yeah. Yeah. Any question before we call it a day?
Sir, can you please go back up?
Up again.
Before
this one or after this one?
Up. Before
Up,
this one.
We mean this one.
Up again.
Up again.
Yes.
Yeah.
Yeah, turn on the recording, sir.
What's wrong with the recording?
Sir.
Sir.
Yes, I'm listening.
Do we
Sir,
have
stop
tutorials,
recording,
please?
sir.
Why do you want me to stop recording?